Deductive reasoning. When my kids were younger, they were 10 and 13 when I wrote the first edition of this book. They occasionally left something at school, such as a jacket, a book, or even a phone. Later, when they were home, one of them might say, "I can't find my jacket." The conversation that usually proceeded was one of retracing steps and trying to remember where the object was last seen. I might offer a suggestion such as, "Well, if it's not in your backpack, then it must be at school." By saying this, I'm essentially inviting a logical deduction. We start with the fact that it must be at one location or another and then look to verify the conclusion. My kids might not realize it, but they are working through a basic deduction problem, and sometimes this deduction process results in finding the missing item. Objectives. On completing this chapter, you should be able to achieve the following: understand the difference between inductive logic and deductive logic, be able to describe what a syllogism is and what the parts of a syllogism are, be able to differentiate between valid and non-valid forms of deductive logic, be able to diagram logical arguments and determine validity using circle diagrams, understand conditional reasoning and categorical reasoning. Deduction and induction. The previous chapter discussed inductive reasoning. Induction involves making predictive inferences from observations. Induction moves from specific to general, based on evidence, and drawing conclusions that are likely to be true. In induction, the outcomes are probabilistic. For that reason, many of the examples in the literature were framed as statements of confidence in a prediction or a generalization. Induction can also be described as going beyond the given evidence to discover something new via thinking. With deductive logic, on the other hand, we are attempting to explain how people make specific conclusions and to determine if that conclusion is valid. Deduction often starts with a general statement, "My jacket is either in my backpack or at school," and then proceeds to more specific statements, "It's not in my backpack." Rather than going beyond the given evidence to discover something new via thinking, deduction often involves verifying that which is already known. The two kinds of reasoning are related in terms of how we use them in everyday thinking. Although the psychology of induction and deduction differ, we tend to use them together, and it can be difficult to tell if you are using inductive reasoning or deductive reasoning. For example, if I buy a coffee from McDonald's, take a sip, and discover that it is very hot, I conclude that McDonald's coffee is very hot. That is a generalization, and I can infer that other McDonald's will serve hot coffee. Categorical induction might even allow me to project the property of hot to coffee purchased at other similar restaurants. In both cases, I am relying on inductive reasoning and past experience to make some conclusions about the future. Suppose, then, that I form a general premise about McDonald's coffee. This premise can be stated as premise: McDonald's coffee is hot. A premise is a statement of facts about something. In this case, it's a statement of fact about McDonald's coffee. A premise like this can be used to make precise conclusions. For example, combined with additional premises and a conclusion, we can create an entire categorical syllogism. Premise: all McDonald's coffee is hot. Premise: this coffee is from McDonald's. Conclusion: therefore this coffee is hot. In a deductive statement, it is assumed that the premises are true. Given these two premises, the deduction is considered to be valid if the conclusion follows on directly from the premises. A valid argument is one where the conclusion is the only possible conclusion given the premises. In other words, there can be no other possible conclusion from these premises. If these true premises allow for alternative conclusions, then the deduction is not valid. It's also important to consider the soundness of the argument. A sound argument is one that is valid, the only conclusion that can be drawn from the premises, and one for which the premises are known to be true. It is possible to have valid arguments that are not sound. In the case above, the argument is only sound if we know that all McDonald's coffee is hot. If there is evidence to the contrary, the argument can still be valid, but it is not a sound deduction, and so we may not trust the conclusions. In the following sections, I consider some examples that show how deduction is used in a simple everyday context. I then consider more complex examples and show how people often fail to consider the parameters of logical reasoning. Finally, the chapter discusses classical reasoning and conditional reasoning in greater detail, and how these are occasionally challenging for people in reasoning tasks. The structure of a logical task. The previous example with McDonald's coffee shows that deduction can be used to arrive at a conclusion about a member of a category, McDonald's coffee. People can also rely on deduction to make predictions about options and outcomes. For example, imagine that you're planning to go shopping at the shopping center with a friend. She texts you to say she will meet you by the Starbucks coffee store or by the shoe store. You have two options that cannot both be true, but one that must be true. This can be stated more formally as: premise, your friend is waiting at Starbucks or by the shoe store. Premise, your friend is not at Starbucks. Conclusion, therefore your friend is by the shoe store. This deductive argument has several components. As with the examples in the preceding chapter on induction, and also with the McDonald's coffee examples, the statement has one or more premises and a conclusion. The premise gives basic factual information that we can reason from and reason about. In a deductive task, we assume that the premises are true. That is a crucial aspect of deductive logic because, in many ways, the challenge of deductive logic is evaluating the validity structure of the task. We will discuss some problems with this idea later in the chapter. Each premise can contain facts and operators. Facts are just what you would expect them to be. Facts are things that can be true or things that can be false, descriptions, statements about properties, and predicates. The operators are crucial to the deduction task, and they are part of what make this different from inductive reasoning. In the example above, the operator or adds meaning to the understanding of the task. This is what allows us to think conditionally about the two alternatives. She is either here or there. One must be true, but both of these cannot be simultaneously true. If you are given information that one of these is false, then you can conclude that the other must be true. Other common operators are and, not, if, all, some, none, etc. Each of these defines the nature of the deduction and can modify the complexity of the argument. The deductive task also has a conclusion, which is usually marked off with expressions like therefore, then, etc. In most deductive logic tasks, subjects are usually asked to assume that the premises are true and then determine whether or not the conclusion logically follows. A valid conclusion is one in which the given conclusion is the only possible conclusion given the truth of the premises. An invalid conclusion is one where the same set of premises can give rise to more than one possible opposing conclusion. Deduction can seem counterintuitive. Although we are constantly making inferences, drawing conclusions, and making predictions about things, deductive logic can often seem counterintuitive. One of the reasons for this is that we may agree with a stated conclusion, even if it is not logically valid. Alternatively, we may reject conclusions that are valid. This is an effect known as belief bias, in which we have a bias to assume that deductions we believe or are more believable are valid, and those that do not seem believable are less likely to be valid. This is a bias because validity is determined by the structure of a logical task and not its believability. And in other cases, we may agree with a valid conclusion, but for idiosyncratic reasons. Consider an example that comes from a paper by Mary Henley, 1962. This was one of the earliest attempts to understand the psychology of deductive logic and thinking. People in Henley's research were presented syllogisms that appeared in the form of a basic narrative and were then asked about their conclusions. Here's an example of a valid deduction. I'll explain later why this is valid and how to verify that. Syllogism. A group of women were discussing their household problems. Mrs. Shivers broke the ice by saying, "I'm so glad we're talking about these problems. It's so important to talk about things that are in our minds. We spend so much of our time in the kitchen that of course household problems are in our minds, so it is important to talk about them." This is a fairly straightforward, if somewhat dated sounding syllogism. Henley asked her subjects to verify if the conclusion, i.e. that it is important to talk about household problems, was valid. She also asked her subjects to explain why or how they arrived at that conclusion. In other words, She asked them to engage in a logical deduction task. She found that many of her research subjects failed to reason logically. That is, they failed to distinguish between a conclusion that was logically valid and one that was factually correct or one they agreed with. These two things are not the same. As we have seen earlier in our discussion of belief bias, Henley referred to this as the failure to accept the logical task. That is, people seemed to place a heavy premium on the content of the anecdote and thus did not reason logically. For example, one person in her study suggested this was not a valid conclusion and said, "The conclusion does not follow, i.e., it is not valid. The women must talk about household problems because it is important to talk about their problems, not because the problem is in their minds." In this case, the person was incorrect to suggest that the conclusion was not valid, and the subject also provided a reason that was based on their own understanding of why we should talk about problems. This is a failure to accept a logical task. Other subjects suggested correctly that this was a valid conclusion, but they gave reasons which suggested that even though they correctly identified it as valid, they were still failing to reason logically. For example, another person said, "Yes, it could be very important to the individual doing the talking, and possibly to some of those listening, because it is important for people to get a load off their chest, but not for any other reason unless in the process one of the others learned something new of value." This subject suggested the conclusion was valid, but again provided an answer that was idiosyncratic and rooted in personal belief. Although the conclusion was correct, this is still a failure to reason logically. One way in which we can evaluate the validity of this statement is to simplify it somewhat and then replace some of the facts with variables. Using variables can help because it allows us to examine the structure of the argument separately from the semantics. Henley's syllogism can be simplified as follows. Premise 1, it is important to talk about the things that are on our mind. Premise 2, household problems are on our mind. Conclusion, it is important to talk about household problems. We can replace the facts with variables as follows. The phrase, it is important to talk about the things that are on our mind, can be rewritten as, it is important to do A. The second premise tells us something else is equivalent to the first fact, and we can say B is equal to A. Premise 1, it is important to do A. Premise 2, B is equal to A. Conclusion, it is important to do B. This shows how and why the logical deduction is valid, and it is a fairly straightforward task as a substitution. Henley's point was that people often misunderstand what it means to be logical. They end up paying attention to the semantics and the content, which is important for understanding people, and tend to ignore or miss the underlying logical structure, even when explicitly asked to do so. Henley noted other related problems with deductive thought. For example, subjects often restated specific premises as being universal. Consider this syllogism. Syllogism. Mrs. Cook had studied home economics in college. Youth is a time of rapid growth and great demands on energy, she said. Many youngsters don't get enough vitamins in their daily diet. And since some vitamin deficiencies are dangerous to health, it follows that the health of many of our youngsters is being endangered by inadequate diet. Subjects were asked to indicate if they thought that it was a valid conclusion to say that the health of many youngsters is being endangered by inadequate diet. Many subjects extended the first premise to be universal by ignoring the word many and restating it as youngsters do not get enough vitamins. In doing so, they endorsed the wrong conclusion. In short, Henley, 1962, noted that people seem not to accept logical tasks as being deducto-logical. They misstate premises, omit premises, and generally fall prey to the kinds of cognitive biases that Kahneman and Tversky would later describe with respect to judgment, inductive reasoning, and decision-making. It is important to note that these results do not indicate the subjects were unable to reason logically, but only that they did not treat this as a logical task, even when directed to. Henley suggested that the problem was that people focused on the semantics and the content rather than on the form of the argument itself, and later were confirmed many of these biases and shortcomings. Johnson Lard suggests that naive reasoners with no training in formal thought may make many cognitive errors in reasoning and yet still manage to achieve their goals and make good decisions. He refers to this as a fundamental paradox of rationality. This is a paradox because rationality should be a necessary condition for correct decision-making and a hallmark of formal, mature thinking, and yet in many ways it does not seem to be necessary at all. Deductive logic is challenging for most people. The fact that we fail can be attributed to both the complexity and abstractness of the tasks, as well as the general effectiveness of many cognitive heuristics. It may be that for many basic decisions and conclusions, logical deduction is not needed, and that the additional resources needed to reason correctly may be suboptimal. Theory in the real world. When I lecture about the psychology of deduction, I have occasionally referred to a movie from 1985 called Labyrinth, and despite being from the 1980s, I am surprised how many students have seen it. It is principally a children's movie, but several parts are interesting for adults as well. I will summarize the plot briefly. At the beginning of the movie, a young girl, Sarah, expresses some frustration about having to take care of her baby brother. It is a fantasy movie. At some point, she wishes that a goblin king will take the baby away. Of course, her wish comes true, and the goblin king, played by the late and terrific David Bowie, steals the infant and hides him in a castle. Sarah can retrieve the baby only if she makes it through a labyrinth. Early in the movie, she is faced with a single passage that ends with 2 doors. One of the doors is red and one of the doors is blue, and each of these doors has a guard who relates the rules of the game she must play in order to figure out which door to open. The game is a version of a classical logical problem known as the Knights and Knaves problem. The guard tells her that one of the doors leads to the castle and the other leads to certain death. They also tell her that one of them always lies and the other always tells the truth. Sarah has to figure out which door to open. In other words, we can state the problem as follows. Premise: either the red door leads to the castle or the blue door leads to the castle. Premise: either the red guard tells the truth or the blue guard tells the truth. If you haven't seen this movie before, you may want to take a moment to find this clip on YouTube. It is easily available. Search for Sarah's certain death riddle, and whether or not you have seen the clip, try to solve the problem. There is a correct answer, and I will give the solution at the end of the chapter. Categorical reasoning. Categorical reasoning occurs when we make conclusions on the basis of category membership. This is also referred to as classical reasoning, because we are reasoning about a class of things. In the previous chapter on inductive reasoning, we also emphasized the importance of categories. In that case, the emphasis was on the similarity between the premise and the conclusion. Strong similarity results in stronger inductions. With respect to deduction, the emphasis is on the actual category membership rather than similarity. An often repeated classical syllogism is the following: major premise, all men are mortal; minor premise, Socrates is a man; conclusion, therefore Socrates is mortal. In the classical syllogism, the standard format is a major premise, which refers to a statement about the category. In this case, we are suggesting that the category men is predicated by the category mortal. In other words, there is an overlap between the category of men and the category of mortal. In the minor premise, the statement offers specific information. In this syllogism, the major premise tells us about the relationship between the two, so that we can transfer the properties of one category to the other. Since all men are mortal and we know that Socrates is a member of the men category, we can conclude that he is also a member of the mortal category. Because of the relationship between the two categories stated in the major premise, notice that there is little role for similarity or featural overlap in these statements. It does not matter how similar Socrates or not is to the category of men. All that matters for the argument is that we know he is a man. There are many different varieties of formal classical syllogisms. For our purpose, we can focus on 4 basic versions. Universal affirmative. The universal affirmative is a statement in which the relationship between the two categories is universal for all members as stated. For example, if we say that all cats are animals, we are using the universal affirmative form. Substituting with variables, we have all A's are B's, as shown in figure 7.1. One aspect of this universal affirmative form is that it is not reflexive, and thus has 2 possible forms. The first, shown on the left, suggests that all members of category A are contained within a larger category B. This suggests a hierarchical relationship such that B is the larger category and A is a subcategory. In this case, it is true to say that all A are B, but the reverse is not true. It is not true to say that all B are A. On the right is the other form of all A are B. In this case, there is a reflexive relationship and everything in category A is the same as members in category B. Figure 7.1, two possible circle diagrams that illustrate the universal affirmative. Particular affirmative. If we say some cats are friendly, we are using an expression known as a particular affirmative. We mean that some members of the cat category are also members of the category of friendly things. The particular affirmative suggests that some members of one category can also be members of another category. As shown in Figure 7.2, there are four possible versions of this statement. Considering the abstract version, some B are A, the diagram on the top left shows a large category B and a small subordinate category A. In this universe, the statement some B are A is true because all of the members of category A are also members of the category B, but there are many other members of the category B which are not also members of category A. At the top right, the diagram shows two partially overlapping categories. In this universe, the statement some B are A is also true because whatever is contained in the overlap between the A category and the B category confirms this premise. Particular affirmative, some B are A. Figure 7.2, four possible circle diagrams that illustrate the particular affirmative. The two diagrams on the bottom are more difficult conceptually. When we hear that some B are A, it is important to realize that the word some can mean at least one and possibly all. The reason is that as long as one member of category B is also a member of category A, the statement is true. Even if all the B's are also members of category A, the statement some B are A is still true. Or think about it this way, if it turned out that all cats were friendly and I said to you some cats are friendly, I would not be telling a lie. This would be a true statement. Some does not preclude all. In the bottom left, the diagram shows a case in which all members of category B are equivalent to the members of category A. Although this is an example of a universal affirmative, it can also be an example of a particular affirmative. The statement some B are A is still true. Admittedly, it is an incomplete statement, but in a universe in which all members of category A are equivalent to all members of category B, it does not render the statement some B are A to be untrue. This is also the case for the figure on the bottom right. Here we see that category A is the superordinate category, and that all members of category B are subordinate. In this case, we can still say some B are A, and that is a true statement within this arrangement of categories. What this means is that the particular affirmative is a more difficult statement to evaluate. It gives reliable information about the status of at least one and possibly all members of category B. It tells you very little about the status of category A, and it tells you very little about the entire relationship between categories A and B. When evaluating a series of statements, for which one of them is a particular affirmative, considerable care must be taken to avoid an invalid conclusion. Universal negative. If we say that no cats are dogs, we are using a statement referred to as a universal negative. The universal negative expresses a relationship between two concepts for which there is absolutely no overlap. In contrast to the universal affirmative and the particular affirmative, the universal negative has only one representation. It is also reflexive. The statement does not tell us much about other relationships with respect to category A and category B, except to point out that these two categories do not overlap at all. See Figure 7.3. Figure 7.3, the only possible circle diagram that illustrates the universal negative. Universal negative, no A are B. Particular negative. If I say that some cats are not friendly, I'm using the particular negative. In this case, I want to get across the point that some members of one category are not members of another category. As with many of the other examples, there are several ways for this statement to be true. In Figure 7.4, we can see three different ways in which the statement some A are not B can be true. On the top left is shown the case where the superordinate category A contains a subordinate category B. This allows for the statement to be true because there are many members of category A which are not contained within the subordinate category B. On the top right, we see the example with a partially overlapping category A and category B. In this example, the statement is still true because there are many members of category A which do not overlap with category B. At the bottom of the figure, a diagram shows a case where the two categories do not overlap at all. Although this diagram also represents the universal negative relationship, the statement some A are not B is still technically true in this case. If it were the case that there were no friendly cats anywhere, impossible, and I said some cats are not friendly, my statement would still be true in this no friendly cat universe. Particular negative, some A are not B. Figure 7.4, 3 possible circle diagrams that illustrate the particular negative. Context errors in categorical reasoning. Reasoning about categories and concepts is a fairly common behavior, but because of the occasional ambiguity and complexity of these classical relationships, people often make errors. In addition, many of the errors we make are a result of conflating personal beliefs and knowledge with the notion of logical validity. One way to avoid making these errors is to use the simple circle diagrams like those shown in figures 7.1 to 7.4 to determine whether or not a conclusion is valid. If there is more than one configuration that allows the premises to be true, but that lead to different conclusions, then it is not a valid deduction. Consider the following syllogism. Premise: all doctors are professional people. Premise: some professional people are rich. Conclusion: therefore some doctors are rich. The first premise tells us something about the relationship between doctors. Let's assume these are medical doctors in the category of professional people. It tells us that everyone who is a doctor is also a member of this category. It leaves open the possibility that the two categories are entirely overlapping, or that there is a larger category of professional people which also includes teachers, engineers, lawyers, etc. The second premise tells us something about some of the professional people. It tells us that some of them, meaning at least one and possibly all, are rich. Both premises express a fact, and in both cases the fact conforms to our beliefs. We know the doctors are professionals, and we also know that at least some of the people in the category of professional people could be rich. The conclusion we are asked to accept is that some doctors are also rich. The problem with this deduction is that it conforms to our beliefs, and those beliefs can interfere with our ability to reason logically. We might know a rich doctor, or have friends or family who are rich doctors. That is not an unreasonable thing to believe, because although not all doctors are rich, certainly we are all aware that some of them can be. We know this to be true from personal experience, but that knowledge does not guarantee a valid deduction. A conclusion is valid only if it is the only one we can draw from the stated premises. This is an example of a cognitive bias known as the belief bias, in which people find it easier to evaluate believable statements as being valid and non-believable statements as being invalid. In this case, the conclusion is not valid, but it is believable. Figure 7.5 shows two of several possible arrangements of the categories. Each of these arrangements allows the premises to be true, but each arrangement also shows how opposing conclusions can be reached from these same premises. On the left, it shows one possible arrangement of the categories, such that the premises are true and the conclusion is true. It shows doctors as a subcategory of professional people, and it shows a category of rich people that overlaps with professional people and includes the doctors. And so in this universe, the first premise is true because all of the doctors are professional people. The category of rich people overlaps partially with the category of professional people, allowing the second premise to be true. Finally, because the category of rich people overlaps with the category of professional people and includes the doctors, it allows for the conclusion to be true as well. This state of affairs conforms to our understanding of doctors as generally being financially well off. Figure 7.5. This is an example of an invalid categorical statement and the belief bias effect. Both sets of circles allow for the premises to be true, and yet they support contradictory conclusions. An invalid deduction. Premise: all doctors are professional people. Premise: some professional people are rich. Conclusion: therefore some doctors are rich. Okay, so on the left you can see that some doctors are rich and professionals, and on the right you can see doctors don't have to be rich to be professionals, so it's contradictory and thus invalid. The problem is that this is only one of many possible arrangements of the classes that allows for the premises to be true. On the right is an alternative arrangement. In this case, the category of doctors is still completely subsumed within the category of professional people, thus allowing for the first premise to be true. This also shows that the category of rich people partially overlaps with the category of professional people, thus allowing for the second premise to be true. However, the overlap between the rich people and the professional people excludes all of the doctors. In this arrangement, both premises are still true, but the conclusion, therefore some doctors are rich, is not. In this arrangement, no doctors are rich. The existence of both of these arrangements, each of which allow for the premises to be true, but make different predictions with respect to the conclusion, indicates that this is not a valid syllogism. Of course, one might protest the conclusion of invalidity, because it is not true that no doctors are rich. You surely know one or two rich doctors, or at least have heard of one or two rich doctors. In doing so, you would be showing a belief bias. That is one of the things that is challenging about deductive logic. This is not a valid argument, and yet the conclusion can still be true. In logical deduction, it is often difficult to separate truth from validity. A related problem can also occur for valid deductions. It is possible to have a valid argument that is unsound. An unsound but valid deduction is one for which the conclusion directly follows the premises, but is still unacceptable. This can arise when one of the premises is false. Consider the following example. Premise: all frogs are mammals. Premise: no cats are mammals. Conclusion: therefore no cats are frogs. In this case, the form is valid and the conclusion is both true and validly drawn, and yet, because the premises are false, the deduction is not sound. Consider another example with a valid structure but a false conclusion rather than a true conclusion, as in the preceding example. Premise: all students are lazy. Premise: no lazy people pass examinations. Conclusion: therefore no students pass examinations. In this case, although one can imagine the second premise being true, the first premise is not true. However, the structure of the task is still valid, and so it does follow from these two premises that no students pass examinations. This is demonstrably false, and so this argument is considered to be valid but not sound. A sound argument is a valid argument that is based on true premises. An argument that is sound guarantees a true, valid conclusion. All of these examples suggest a clear limitation for deductive reasoning within the scope of human thinking abilities. Johnson Laird, 1999, suggests the main limitation of deduction is that it really does not allow one to learn new information because logical arguments depend on assumptions or suppositions. He suggests deduction may enable you to arrive at conclusions that were drawn about evidence that is present, but it may not add new information in the way induction can. Deduction allows a person to test the strength of their conclusions and beliefs. Induction allows a person to acquire new information by thinking.